Hi, I'm Devin Ron, and I'm representing Team Dryer Desire for the 2022 Spring Capstone competition. My teammates are Lauren Tapp, Tara Fahey, Michael Din, Ben Crow, and Jose Mahouf. Our sponsor is Ambo Farmers Voice, and we've been working closely with Dr. Zama, as well as villagers, farmers, and solar dryer builders in southern Cameroon and Nigeria. Currently, villagers lack the means to preserve foods effectively, which forces farmers to sell crops at peak harvesting seasons. This drives selling prices down at market and increases food waste due to high supply and not enough demand. There is a need for more hygienic, effective, and consistent solar drying methods and designs for rural Africa.
Our target location for the solar food dryer is in southern Cameroon and is designed to be used by rural individual farmers. The motivation is to decrease drying times and increase both effectiveness and consistency, with an emphasis on retaining food quality and nutrition compared to current solar food dryers. A major challenge in design was keeping the complexity of the build low enough to be made with local materials and tools in rural Africa, while also keeping the cost under $150. A villager named Emmanuel was able to provide us with a list of materials available for prices for when he builds solar dryers. Current drying times range from 3 to 5 days depending on the fruits and weather conditions. A big issue is drying food during the rainy season. Hot and humid weather is the perfect conditions for food spoilage, so minimizing moisture in the system is a must. The chosen design draws heavy inspiration from the chimney design, but features an angled solar collector to increase solar incidence and air velocity, as well as vertically stacked trays to avoid direct sunlight, which is a cause of nutrient and color loss. Our team designed the dryer to have a maximum tray height of 5 feet in order to be comfortable to use by an African woman, which is our most likely user. CFD simulations were used to model the airflow of different solar collectors to drying chamber designs. This was also used to determine the fan placement and model the airflow and uniformity inside the drying chamber. From this information, we were able to finalize our CAD model and create an instruction manual that will be sent to villagers in Africa, detailing the dimensions of parts and steps to build the solar food dryer. For testing, the top tray is suspended and connected to a force gauge. Tomatoes were used as a control fruit. It is assumed that the tomatoes are originally at 95% water content, and the test dries were considered done when 20% water content was reached. A temperature and humidity sensor was also used as well to track the inside conditions of the dryer throughout the day. We also attempted to dry a range of fruits to show the system is robust. Tomatoes, pineapples, papaya, mangoes, kale, oranges, lemons, grapefruits, and limes were all dried successfully. Mangoes are harvested mostly in the rainy season and are commonly dried and consumed in Cameroon. The dryer handled these extremely well with no spoilage and very good flavor retention. Pineapple took the longest to dry, but similarly to the mangoes, had no spoilage and a fantastic flavor. These were our team's favorite fruits from testing, and we decided to dry some the day before to bring to Capstone Expo. Our first passive test was significant for targeting improvements that were made for the future tests. Our problem was 1/3 of our tomatoes had spoiled, which is unacceptable for our product's goals. We learned that cutting more thin slices gets each slice to a state less prone to spoilage more quickly. We also needed a method to dispel condensation and keep flies and bugs out of the system. Changes were made to poke small holes in the bottom of the dryer for drainage, and bug netting was placed at the inlet and outlet to prevent insects from entering the system. Most importantly, we learned the significance of weather conditions. The first day was great weather, about 70 degrees Fahrenheit and dry, while the second 2 days were hot and humid with periodic showers, aka ideal conditions for bacteria to grow and food to spoil. This was a great test for the rainy season conditions, but improvements had to be made to achieve our dryer desire. Our second test was active with fans running on a dry 60-degree Fahrenheit day. Fruits were put in the dryer at sunrise and finished at sunset after 9 hours. This emphasizes the effectiveness of active components along with sunny, dry weather. Additionally, there were no insects or evidence of condensation pooling after the upgrades made because of the first experiment. After finding success with the updated dryer, we lowered the requirement for drying being finished from 20% to 12% water content and reattempted a passive and active experiment with bamboo charcoal at night to try and lower humidity. There's a trend for high temp and low humidity during the day and low temp with high humidity at night. It can also be seen that virtually no drying is occurring at nighttime. This is because the temperature must be at least 85 degrees Fahrenheit to be drying. For reference, the ideal temp for drying leafy greens is 120 degrees Fahrenheit and 140 degrees Fahrenheit for fruits. The second passive test had a 47-hour decrease in drying time from the first, once again highlighting the importance of good weather conditions. A 30-hour drying time is a pace for farmers to start drying new fruits every other day. This time, the active system with fans was finished drying the following morning after a late start, taking 23 hours. This is on pace for farmers to start drying new fruits every day, effectively doubling the efficiency of the solar food dryer in terms of output. The team is going to continue testing for the effectiveness of bamboo charcoal as well as best practices for opening and closing the system's inlet and outlet. For all tests shown, the system was closed during the nighttime and poor weather conditions like overcast, rain, and high humidity. Currently, our solar dryer outpaces current designs with 1 to 2 day dries in fair conditions, compared to 3 to 5 day dries with solutions in southern Cameroon and Nigeria. The cost of building the base passive solar dryer is estimated to be about $84 with local material costs, yielding return on investments of about 3.3 months. Adding solar panel and fans for the active system increases the price to $219, with a return on investments of about 8.5 months. Additionally, it is estimated that the passive model can increase profits by $308 per dryer per year, and the active system could increase by $800 per dryer per year. This shows that solar food drying can be economically beneficial, and that active components are worth the upgrade despite high initial cost. Thank you to our sponsor Amba Farmer's Voice and Dr. Isaac Zama, as well as our boots on the ground contacts Emmanuel, who was helpful for building materials and costs in Cameroon, Priscilla, who shared knowledge and challenges regarding the chimney dryer in Nigeria, Pa Ojong, who shared his experiences operating solar food dryers. Also, thank you to Dr. Colton for guidance and resources with respect to solar drying, and our instructor Dr. Simmons for advice and project oversight throughout the semester.